So I was rushing out the door this morning, grabbed my travel mug, and immediately burned my hand on the scalding hot coffee.
Oh, no.
Right. And as I'm doing that, that classic hot coffee hand flap band.
I know the exact one.
Yeah, and I'm looking at my phone, which is sitting at a dismal 2% battery. And I just had this absurd thought.
Let me guess. Wishing you could charge it with the coffee.
Exactly. Like, wouldn't it be amazing if I could just use this annoying radiating heat to actually charge my dead smartphone?
It makes a lot of sense conceptually.
Well, for anyone who loves learning and is curious about the wonders of the universe, you are in the right place. Welcome to Intellectually Curious.
Glad to be here for this one.
Today, we are doing a deep dive into a stack of recent MIT and NREL research papers to figure out exactly how close we are to making my coffee charging dream a reality.
And we're talking about thermophotovoltaic energy conversion, right? Or TPV.
Spot on. Okay, let's unpack this. Our sources outline that TPV bypasses traditional mechanical turbines completely. It captures the infrared spectrum emitted by high-temperature heat sources directly via specialized photovoltaic cells.
Which is a huge shift from how we usually generate power.
It really is. But hey, before we get into the exact mechanics of those cells, a quick nod to Embersoak, who is sponsoring today's show.
Definitely.
Need help with AI training or automation or integration or software development? Uncovering where agents could make the most impact for your business or personal life, check out embersilk.com for AI needs.
So getting right into it, what's fascinating here is the key difference from the solar arrays you might have on your roof. It's all about the targeted spectrum.
Because standard silicon panels are basically just optimized for visible light, right?
Yeah, exactly. They capture visible light from the sun, but they essentially waste lower energy infrared photons. They just lose that heat right to the environment.
Right. Which brings up an obvious question. I mean, if standard panels are wasting this infrared heat, why haven't we just been slapping different materials onto traditional solar arrays this whole time?
That's the logical next step, yeah.
So what was the major bottleneck holding TPV back until these recent papers?
Well, the bottleneck was mostly about material band gaps and thermal loss. You need a semiconductor that is precisely tuned to capture lower energy infrared photons.
Ah, okay.
And that's where materials like gallium antimonide come in. Unlike standard silicon, it has a narrower band gap tailored to absorb those specific infrared wavelengths and turn them directly into electricity.
That makes sense. And that ties into the 2022 MIT and NREL breakthrough, right?
It was monumental because they finally managed to hit 41% efficiency.
Wow.
Yeah, they achieved this by engineering a cell that not only captures the right photons, but uses a highly reflective backing. So it bounces the unabsorbed lower energy photons right back into the heat source to keep it hot.
Here's where it gets really interesting, though. That is a brilliant engineering pivot, but the momentum didn't stop there.
Not at all.
By May 2024, another team reached an astounding 44% efficiency using a silicon carbide heat storage material.
44% is just incredible.
It really shows that instead of just looking for entirely new energy sources, we're getting much better at eliminating waste from the ones we already have.
Exactly. And when you look at the macro applications, this could completely redefine grid storage.
How so?
Well, instead of relying solely on massive, expensive lithium-ion battery banks, you could use excess electricity to heat an insulated block of graphite or molten tin to over 2,000 degrees.
2,000 degrees, wow.
Yeah, really hot. Then you use these highly efficient TPV cells to convert that stored thermal energy back into electricity perfectly on demand.
That's amazing.
It's an elegant, solid-state solution with no moving parts. And researchers claim it could be much cheaper than lithium-ion batteries. Plus, the aerospace industry is actively developing this to create incredibly reliable power systems for deep space exploration.
So what does this all mean? To me, it's just a great reminder of our capacity to solve complex problems. We're continually finding ways to squeeze every drop of potential out of the systems around us, driving some truly inspiring technological progress.
It's an amazing trajectory, and I'll leave you with this thought to mull over. If we can efficiently turn heat back into electricity using customized semiconductors, what happens when everyday objects, from your laptop to massive industrial machinery, start recycling their own thermal glow to continuously power themselves?
If you enjoyed this podcast, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.